at Sunway University. He is also working with Lancaster University as a full professor. And most importantly, he is currently our visiting professor in the Department of Mechanical and Manufacturing Engineering, UPM. Previously, he was a chair professor at the Center of Research Excellence in Renewable Energy at King Fahd University of Petroleum and Minerals, KFUPM, Saudi Arabia. Prior to joining KFUPM, Prof. Saidur worked for 18 years in University of Malaya. He completed both his PhD and Master in Engineering Science from University of Malaya, Malaysia. For the years between 2014 to 2020, Cleverite Analytics has awarded him Highly Cited Researcher for being among the top 1% researcher with most cited documents in his research field. He has also achieved Highest Accumulation Citation Award from University of Malaya from 2011 to 2014. Prof. Saidur also won Vice Chancellor's Award for Achievement in Research from Sunway University in 2019. He has published more than 500 journal papers, mostly in top-ranking journals. He is ranked #1 by Web of Science on nanofluid research-related topic. He has more than 44,000 citations with a H index of 109, according to Google Scholar Citation. He has supervised more than 80 postgraduate students so far and has secured and managed more than 25 million ringgit research grants. On the topic of MXene, he has published more than 30 papers on the MXene synthesis, characterization, and applications in energy storage, heat transfer, and solar energy harvesting. Prof. Saidur also have built state-of-the-art lab facilities with high-end lab equipment to synthesize, characterize, and perform investigation on MXene performance. Currently, he is supervising more than 10 PhD and master students on MXene synthesis and their applications in energy storage, heat transfer, solar energy harvesting, fuel cell, and thermoelectric. Such a high achievement from Prof. Saidur Rahman. We're honored to have you with us today, Prof. So without further ado, I would like to invite Prof. Saidur to share his knowledge with us. Prof, the Zoom page is yours. Prof, you may start.
Dr. Zul, I'm in organizing team to organize this event. So basically, I'm going to share some of my experience as Azma highlighted. We have a research center for technology. I'm leading the mostly I will be so far some of our activities on this new research behaviors, what lab, how these materials can be synthesized, how it will be sharing with some. Obviously, I have a number of participants from UPM and maybe from other universities as well. So let's get started, understand these topics. So again, there is another phase of the next phase from this. We call it production to application cycle. As you can see, this can be produced by tube furnace, as you have seen at the bottom of the slide. So using tube furnace with stoichiometric, with produced in the form of a big shape, and then motor vessel carried out composition, structure, and then we can apply transfer light. I will show what are the applications of these materials. So, there are other materials also invented sometimes back. As we know, CNTs were invented by Japanese scientists in 1991, then graphene in 2004, and MXene was invented recently in 2011. So many of you might be interested to know how it looks like. Okay, so this is basically a two-dimensional layered materials. Okay, that is one of the key points we need to understand. So from the figure, as you can see, so it has both length and breadth. But most importantly, why it is called nanomaterial? Because it's, as you can see in one of the figure. So I have taken all this from different sources. In one of the figures, as you can see, that its thickness is 1 nanometer. So that's why it is called two-dimensional layered nanomaterials. Okay, due to its surface and also the interlayer spacing, many other materials also can be embedded, can be intercalated, can be inserted, can be doped, meaning heterogeneous structures case area is used. Terminals like oxide, chloride, hydroxide terminals in the form of TX, you can see. So terminals has some added benefit also, can be added there, can be included there. And also you can see its structure is like accordion-like play. So in between there are spaces. So a lot of things can be done in between that spaces. Okay, and there are SEM images, TM images, as you can see here. So this is how it looks like. Now, how we can understand is the most basic things how we derive. So if we need to understand this MXene, we need to understand the max space. If we need to understand the max space, we need to understand the periodic tables. So in the periodic tables, as you can see, there are M elements, there are A elements, there are X elements. Okay, so these are the precursor materials which are with the specific chemistry, stoichiometric combined, and then put into tube furnace with specific temperature, pressure, ramping and different settings, and then basically max phases are produced. So max phases were invented in long time ago in 1960. Invented recently in 2011 by Yuri Gogosi. So there are varieties materials can be X elements basically carbide and nitride. So there are varieties of materials compositions can be produced from these figures. And also there are N also can be changed. I think I will show that in one of the slides. So these are the precursor materials available from different vendors. Okay, we can purchase them, and also MXene is also available commercially, but not MXene. There are some Chinese companies, some other supplier, but sometimes purity is a big question. Okay, through collaboration, maybe some of researchers are getting. So basically, MXene is available quite some time back. I think now almost 60 or 100. I don't know exactly. Okay. So once max phases are there, then this layer is need to be eliminated. That is called scientifically in chemistry term is called etching. Okay, that is called etching using hydrofluoric acid. that A layer is broken, the A layer is eliminated, and then finally we get Ti3C2. That is MXene. So this is the formula for MXene. This is one types of MXene, and most extensively studied, discussed, researched this Ti3C2. In one of the slides, I also will show the discovery of other MXene and max phase materials. Okay, so this is all about max phase precursor materials, and then finally how we got MXene. Okay, so MXene is basically derived from max phase by eliminating A layer through the etching process.
I'm sorry, Prof. Saidur, but we do experience a little bit of lagging. Maybe we can try to
You can see.
Prof. We do experience some lagging. Maybe you can try turning off your video. Maybe it will help with the lagging time of the audio.
Okay. So is that?
Yeah, it is a little bit better now. Yeah. Yeah, yes, Prof. Sorry for the inconvenience. Thank you.
Maybe I change the space. Maybe I go close to the router. You give me 2 minutes.
Okay, sure, Prof.
Yeah. Just wait for one.
Okay.
Yeah, Dr. Asma, I changed the location. Maybe now signal is better, stronger. Is it now?
Okay.
Is it better?
You sounded better. Yeah.
Okay. Yeah.
Thank you.
Yeah. Okay, let me get started again. So as you can see, the discovery started from 2011 and until 2019. Maybe recently also there are some new materials, but this is until 2019. Many other magazines are developed, meaning that different behavior, different performance, different properties can be obtained through these different types of magazine materials. So there are varieties. Okay, there are a lot of discoveries can be done over here. So many basically have a question also in their mind, and even we also had a question in our mind. What is the difference between graphene and magazine? So no material is basically perfect. So that's why different materials, CNTs, graphene, now magazines are developed. So graphene has some of the drawback like low band gap, which is useful for solar energy or light absorption. So band gap is 0 for graphene, whereas for magazine, it is very, okay? It can be very. Graphene's electrical conductivity is also low, whereas magazine has very high outstanding electrical conductivity. So that one I'll share in one of the slides. Graphene is hydrophobic, that is dispersion, mixing behavior, colloidal behavior with some of the water and some solvents, whereas magazine is hydrophilic. Graphene also has low bending rigidity, so that is a mechanical strength. In some applications, high rigidity, high mechanical strengths are required. So there are many more. I'm just highlighting here a few. So there are differences, and also the structure, morphology, many differences are there. So I'm just highlighting here some of the behavior magazine has better than graphene. Also at the bottom, you can see there are various etching methods. So initially it was done by hydrofluoric acid. That was quite hazardous, as you know, the hydrofluoric acid. So there were subsequent the green synthesis, molten salt, and many other top-down, bottom-up, many papers already, review paper, original public papers already published on different types of synthesis. So as you can see, there are tremendous inventions, growth is going on in terms of varieties of materials, in terms of varieties of synthesis approach and method. Okay. So this is also I have taken from Scoopers, as you can see the growth. So it was started from 2011, from 2013, as you can see. Now there are tremendous growth of publications, and mainly major publications are by Yuri Gogursi and his group. Basically, I think the Yuri Gogursi, who is the inventor, who basically came out with that idea of removing that A layer. Okay, so this is a pioneering invention by him and his group. This slide basically shows how this aluminum layer is removed. As you can see, there are aluminum layer, but that is basically the purpose of etching by using hydrofluoric acid treatment. That is the initially Yuri Gogursi and his group used hydrofluoric acid with certain concentration. Now there are many other etchant already invented, used, tried. Okay, in our lab, we now use mild or moderate etchant compared to hydrofluoric acid, that is hydrofluoric acid and lithium fluoride. So some salts, molten salts, these are one ways of synthesizing MXene. So by this etchant, as you can see, one of the layer, aluminum layer is removed and then sonicated, and then MXene sheets are produced by subsequent processes, purified and so on. As you can see, they are bonding also in max phases, how their bondings are there. So compared to other bonding, so this aluminum bonding is something Yuri Gogursi came out with that density functional theory that this can be eliminated. So this is how he did theoretical calculation, and then he used experimental approach to remove aluminum layer. So this is how etching process is done to remove the one of the layer, that is A layer. This is our in-house facilities. As you can see, some small probes, precursor materials. Okay, we got some of the precursor materials from Sigma, Rich, or other vendors. We procured them. Lithium fluoride, aluminum powder, all this we procured. We have in our lab. So our staff, I'll talk later on. So our staff, our team members knows what's are the stoichiometric, what's are the composition. So they mix them and then they put into a tube furnace, as you can see at the right hand side. So we have a research fellow, Dr. Tan, who is synthesizing this. He recently attended 6 days workshop with Yuri Gogursi's group. Previously, we had a PhD student who is basically pioneer who helped us to develop initially these materials. We work together and we develop, and now Dr. Tan is working with us to synthesize this MXene using this tube furnace. We can develop max phase, and then reaction is taken place in the fume hood. Okay, so with this tube furnace, we got the brick phase, brick shape max phase, as you can see at the bottom. This is in our lab. We produce this max phase. Okay, and then using water and pestle, we made into a powder, and finally chemical reaction is taken place at the fume hood. Okay, so this is where is very critical, and this is basically the Yuri Gogursi invented this step. This chemical reaction is very tedious, very complicated, and need to be well maintained. So many people ask, we have a lot of problem, impurities, oxidation, because this process actually need to be maintained very in a stringent way. So if some of the process procedures are not maintained here properly, I think there will be impurities. MXene, good quality MXene cannot be produced here. So this is where the Dr. Tan and my PhD student also learned how to develop the reaction appropriately, properly, so that there are less or no impurities at all. Okay. So these are some of the small probes and some major probes also. During the chemical reaction, as you can see, we have hot plate. So its purpose is to maintain temperature and certain speed, which are required. We also have lithium fluoride salt, as I mentioned, hydrofluoric acid. So these are mixed, poured, combine, okay, and then chemical reaction takes place, as you can see in this previous slide. Okay, so once chemical reaction takes place after a few days or few hours, it's taken out and impurities are removed through washing, filtering, centrifugation, all those processes are there. And finally, we also do SEM, EDX, XRD, TM, FSM, basically is the characterization to see whether MXene is pure or not, okay? So that is about the MXene, but whether it is MXene, graphene, pristine materials are really not perfect. They always have certain drawbacks, challenges. So to overcome, to improve all those challenges, these are called the tuning the behavior of pristine materials. So how this can be done? So this is also another highly potential area. A lot of works going on. A lot of works also can be done in this area, in these topics like hybridization, intercalations, functionalization, surface modification. So all these things can be done. And it's already done in some of the works in the literature. So what is the purpose? Again, is to improve the material's behavior, performance, properties. Okay, how this can be done? By using different types of solvents. Those who are chemists, probably you are better familiar with this. They are known as DMF, TMAOH, TMSO, DMSO, and so on. So there are some solvent by using all those solvent treating. So hybridization, intercalation, surface modification, functionalizations can be done to improve their behaviors and properties. Is it better now, Dr. Asma?
Yes, Prof, much better. Thank you.
Okay. Okay. So this is another hybrid engineering. As you can see in some applications, these materials can be hybridized. So these are called hybrid engineering, interfacial engineering, atomic engineering, termination engineering. So all these can be done with the pristine materials. In some cases to improve the conductivity, facilitating the mass and ion transfer, exposing more active sites, tuning the absorption behavior, accelerating the charge transfer, adjusting the lattice geometry. So this hybrid engineering, hybridization engineering can be done to improve some of its behavior properties. This is in a simple way, what is the definition of intercalation, unique characterization of those materials, accommodate various ions and molecules within their layers is known as intercalation, okay, in between layers. So that's the one of the benefit of the layer structure. So it can be vertically, it can be horizontally. So many works are already in the literatures to improve some of the behavior through this intercalation approach. These are called the terminals, different types of terminals, OH, oxide, chloride. These are the terminals also. Some beneficial effects are associated with these terminals, can be done during the synthesis process also. It's denoted by TX. Various types of shades also, as you can see, the nano shades, nano sheets, nano flowers, nano ribbons, quantum dots, nanoparticles through oxidation, chlorination, solvothermal, different approach this can be done. For example, porous nano sheets, sorry. For example, porous, the metal organic framework where ion can be or gas can be absorbed. So these are good to improve the surface behavior, to absorb some of the pollutant. So this can be done also. Porous structure can also be developed. These are some of the ways of modifying, improving the behavior. As you can see, the interlayer modification, intercalation, as you have seen in earlier slides. So metal ions, organic molecule, molecular cations, surfaction solvents. So this can be done. As you can see, the structure also and the function. Surface modification also can be done. constructing heterostructures. So with other materials like MXene with graphene oxide, polymerization, all this can be done. As you can see, the associated change in structure, function. So all these things these are some of the unique things can be done with the MXene. As you have seen with the formula of the MXene, Mn plus 1 Xn Tx. So I think with this changing in the number also, different layer can be done, and there are associated benefit with this also. So this is also another uniqueness of this MXene materials. Now I'll be talking more about the application. As you can see here as a summary, but there are many other new applications as well reported in the literature. Initially, when MXene was invented in 2011, as you can see, the major share is basically on the energy side. And in energy side is basically to overcome some of the challenges of electrochemical energy storage. As you can see, it is good material for lithium ion, sodium ion, lithium sulfur batteries. Okay. Energy harvesting, textile, flexible energy storage. So basically, it is one of the highly potential material for electrochemical energy storage. Recently, there are works also going on thermal energy storage as well. So it is also good material for catalysis, so hydrogen evolution reaction, oxygen evolution reaction, even hydrogen storage also. It is important material, some works going on. Carbon dioxide reduction, carbon dioxide absorption, electronics application, electrical, thermal, optical, biomedical, biological, antibacterial applications, environmental, sensors, others. As you can see here, electronic, sensor, optics, biomaterial. So it has diverse applications due to its outstanding behavior and properties, structure, properties like electrical conductivity is extremely high. Its thermal conductivity is also good. Catalytic behavior, photocatalytic, electrocatalytic, thermocatalytic, all types of catalytic behavior is also reported to be good. Optical behavior, band gap, energy storage, mechanical behavior, in some cases to make the material stronger, for example, in membrane, so their structure should be strong. So mechanical behavior is also need to be good. And this material has good mechanical behavior as well. So as you can see, it has diverse application. So in thermal area where we are working, this is also our focus centers focus, where we are working in the thermal management heat transfer application. So some of our PhD students also working with the UPM in this area, heat transfer area. So thermal management is one of the challenges even in the battery also. There are thermal runaway in the car radiator. There are thermal runaway. Mobile can be overheated during the charging, discharging process. Solar PV panel also can be overheated, and this may reduce the performance of the solar panel, PV panel due to overheating. So this is where thermal management is. These are some of the applications. There are many other applications where thermal regulation, thermal management also important, and MXene, graphite, and other materials with their combination can play a great role also to improve their to overcome some of the challenges. Heat transfer fluid is an important area where different types of nanomaterials, including MXene graphene, can be used, and there are research going on. So far, a lot of research is going on low temperature, something like 60-70 degree application. But in our case, we are trying to focus on high temperature. So that's how also we built our lab. This is also one of the uniqueness, but this is quite challenging to investigate behavior, properties, developing setup. It's quite challenging at high temperature. Okay, so there are many heat transfer fluid. I think the mechanical engineer, thermal engineer, and chemical engineer basically can work. Researcher can work in this area, suspend the materials, and one of the challenges with these types of fluids are the stability. So a lot of works need to be done, can be done in this area. So one of the question is why basically we are talking about the nanomaterials, nanofluid or heat transfer fluid. So basically these types of heat transfer fluid, as I have shown earlier slide, has very poor thermal conductivity, that is heat transfer behavior. Poor thermal conductivity is meaning that heat transfer rate is poor. Okay, so heat cannot be transferred faster rate. So these are the challenges. These are the limitations of the heat transfer fluids. Water, ethylene glycol, as you can see at the left-hand side. Whereas nanoparticles, different types of nanoparticles, they are solid particles, their thermal conductivities are high. As you can see, single wall carbon nanotube graphene. Graphene has 5,200 or 5,500 thermal conductivity watt per meter Kelvin. That is extremely high. MXene also, we did some work, we found its thermal conductivity is also high. So when these solid particles are suspended in liquid or heat transfer fluid, basically heat transfer performance, heat transfer coefficient, other parameters will be improved. That has been found in the literatures and also based on our initial investigation. So that's why the nanomaterials, nanoparticles are needed. One of the good behavior is the thermal conductivity. Another important behavior or uniqueness of the nanomaterial is the surface area. Many of us we know bulk material, as you can see, compared to bulk material, nanomaterial has more surface area. And this MXene, as you have seen, it has interlayer spacing. It has large surface area, two-dimensional surface, basal plan, and because of that, surface area is also high. And this is also another unique benefit, as you can see, based on some of our references. Some of the literature, as you can see, with the metal organic framework, its surface area is extremely high, 6,240. Okay, so this is also another unique behavior. It's not only for heat transfer, many other energy storage performance behavior also, it is important, this surface area. So these are some of our thermal conductivity results. We conducted some experiment with some of the oil in our lab. We found a good improvement. Okay, 68%, 40% improvement, which are published in good quality journals. Okay, so this not only in this heat transfer area, but in chemical reaction catalysis purpose, this thermal conductivity also plays a great role. Viscosity, which is also a flow behavior, is also important. It should be reduced. So viscosity reduction also found in this case with a low amount of nanomaterials. So this is also another outstanding findings. Normally graphene, MXene, two-dimensional molybdenum sulfide found to be super lubricant friction reduction materials. Recently, I also attended one seminar by Uri Gover's group, and they showed that outstanding behavior of MXene and compared with other materials also. So this is also one of the good behavior. This is important for pumping friction factor. So to reduce friction pumping power, this viscosity behavior is also important. This is at high temperature solar thermal applications where energy storage behavior also can be improved, like molten salt has low energy storage behavior. So if MXene particles, graphene or other nanoparticles are suspended, so this energy storage and thermal behavior, as you have seen, and also they have high melting point. So if this behavior can be improved, this also will play a role to develop utility scale energy storage behavior. Large scale energy storage can be done because molten salts are cheap. Okay. This is also important area for hydrogen energy, as many of us know that hydrogen energy is also clean energy, but its storage is also very challenging. So this hydrogen energy also can be stored by nanomaterials. The MXene has been found one of the potential materials. Some theoretical research is going on, some experimental research also going on. That is called the mechanism called adsorption. Through adsorption, hydrogen molecules can be stored there, but still there are a lot of challenges that need to be overcome. So a lot of work basically, as I have shown earlier, is going on battery. because as you know, the battery energy storage has low energy and power density, electrical conductivity, sluggish reaction, costs are high. As you know, lithium-ion battery is still expensive. Fast charging, discharging, these are also for electrical vehicle is also challenges. Lithium-ion also has fire hazardous availability. You know, it's not abundant. So utility scale energy storage with the lithium-ion battery is also quite challenging for heat transfer energy storage. So these are some of the challenges. So that's why new materials need to be developed, and MXene is one of the candidates. So this is MXene in cathode and in anode applied to improve their behavior. I have taken from literature. So these are some of the energy storage behavior we found in our lab also, with some frictions material. Okay. This is important slide I have taken from literature. So this is actually one of the outstanding behavior of MXene reported. So electrical conductivities for ion movement, ion transfer, charge transfer, this behavior is very important. As you can see, various types of MXene and they are corresponding electrical conductivity. So what I can show here, highlight here, that it can be up to 24,000 Siemens per centimeter. That is extremely high compared to other types of nanomaterials. As I highlighted, graphene has 351, 1,000, 2,000, something like that range. Whereas MXene has extremely high electrical conductivity. Okay, so this is one of the outstanding behavior that plays a great role for electrochemical energy storage, that is in battery, supercapacitor, fuel cell, so on. So mechanical behavior, as I highlighted, in some applications, in catalyst application, mechanical properties for long durability, stability is also important. And also it is extremely high, as you can see here. So to avoid when it is subject to intense pressure, bending, twisting, in that case, I think this bending, rigidity bending behavior is important. And for MXene, it is found to be excellent. Okay, in recent one of the seminar, I noticed that its bending rigidity is extremely high. 49 electron volt of MXene compared to graphene, as you can see. So these are some of the comparison also I'm showing in relation with graphene. So interlayer spacing, this is also another unique benefit. As you can see, in between the layers, some of the particles, molecules, gas can be trapped when MXenes are compounded with other materials. MXenes with layered structure can provide more channels of ion movement. Other materials uniformly adhere to grow between MXene sheets, expanding MXene layer space. So this is also another important, unique features of these materials, make it important, useful. So these are summary. In addition, thermal, electrical, ionic energy storage behavior, I think it also has high corrosion resistance behavior, high temperature behavior, hydrophilicity, flexibility, plasticity. So there are many other unique benefits with these materials. Now, question is whether these materials can be produced in a large scale, production scale, okay, in the industrial scale or not. So in our case, we produce in the lab scale 1.5 gram, 1 gram, because still we are growing and it's also very challenging and it needs a lot of funding, a lot of effort, a lot of human resource needed. So we started with 1 gram. As you can see here, Yuri Gogursi and his group already synthesized, developed this reactor. You see the large scale production, for large scale production, 50 gram. There are report also 100 gram in the lab, Yuri Gogursi and his team. And most importantly, as you can see, the Murata manufacturing industry, Japanese company, actually manufactured 1 kg industrial scale level. So I think a lot of research is going on due to its unique behavior, varieties of materials, structures, properties. So a lot of interest going on, as you have seen, publication is also surging. So I think the industrial scale production, large scale productions are in progress. So cost is also very important because nanomaterials are still costly. So there are alternative routes, approaches, some of the researchers are doing, and this is also in our mind. If this can be done, if cost can be reduced, we think, I think the commercial viability will be extremely high. Okay, so there are some research going on, some of the Urigogo system members doing basically using scrap tire derived carbon can be produced. Maybe in Malaysia, there are other local sources of different materials. As you have seen in the periodic table, precursor materials, if cheap precursor materials can be produced from waste materials or recycled materials, I guess maybe through this cost can be reduced significantly. So this is also another area where a lot of research can be conducted, can be done. Okay. These are some of our works. We started research in our lab in 2018 November. Our lab was ready, and 2019 was our best year. We produced some good quality data through our collaboration, through our PhD student, through our research fellows, and we published in good quality journal through which we developed our expertise. And we are first in Malaysia successfully synthesizing, developing, and publishing good quality, good number of papers. And now we are also supervising students from UPM, UM, Taylor's University, Monash University, UTP, UMP in this area, because it is a potential area, and particularly the thermal area is not focused much since we are good. We have some experience in thermal area, so we are trying to focus in this thermal area. So this is basically our focus, our center for collaboration purpose might be useful. Emerging nanomaterials, MXene graphene scientists, and their hybridization intercalations. So we also have staff. Dr. Tan is also with us here. So in case if additional top-up needed, he also will be with me to answer some of your questions. Energy storage is also our focus, electrochemical, thermal, as you have seen, heat transfer, solar energy. So these are our focus. We are working in this area. Of course, research is a multidisciplinary. This is also the purpose. We are trying to share whatever we have learned, we have acquired, we have gained knowledge. Of course, there are other peoples like chemists, material scientists, researchers. We all work and work together to overcome some of the challenges. So I'll be now sharing some of our facilities. In order to do good research, quality research, we need outstanding facilities, state-of-art facilities. This is one unique things at Sano University. This is also the reason I joined Sano University. So we built this lab by spending 5 million Malaysian ringgit. We built it within 6 months. How strong support from Sano University, as you can see, even though private university, but research support is tremendous. Okay, so these are some of the high-end equipment. As you can see, DSC, TGA, centrifuge, tube furnace, solar simulator. Okay, so these are some of the equipments to check the behavior of the materials properties in our lab. This is our wet chemistry area where the students, collaborators, researchers can work, can develop, can prepare their samples. Okay, can mix. There are sonicators. There are some of the small equipments here. They can work here. This is the fume hood where MXene synthesis reactions takes place, as you can see, and also safety related. So health and safety is also the prime issues. We take care of that because we have to go through audit process also. Well maintained, neat and clean. We also have lab executive to maintain the lab matter. We also have necessary consumables, materials, burette, pipettes, as you can see. Use materials we already have. So we can support collaborators. We can work with the collaborators to supply, to help you with the necessary things as much as we have. This is also another area we call it sensitive room, need to maintain temperature and humidity. Okay, so some of the high-end equipments are here. We have SEM, that is to check the purity, to check some of the behavior of MXene. Some other materials, behavior, characteristics, performance can be investigated using the equipment we put it here. We also have a PhD program on sustainability, science, and technology. It is very popular so far, running very well. We just started. So we have good number of students. Sometimes there are funding, sometimes tuition fee can be web. But I think return on investment also will be good. Okay, so overall, it's a good program. So we invite some students to work in this PhD program. You can find me because time is limited. I always cannot share each and everything here. I'm happy to share all these things in LinkedIn, Facebook, YouTube. Some of my contents are already there. Last year, I gave a presentation with UPM. All those are broken into small content and presented, already loaded uploaded in YouTube. So you can find various contents on research publication related content there. You can listen the recorded video at your convenient time. And time to time, I post some of the research related my experience, research publications, content similarities, self-citations, many other research related my experience, my 23 years of research experience, some of the unique experience I basically share for the sake of early career researchers, junior researchers, okay, for their benefit, because I have some experience throughout these 23 years. So I share, and I hope all this will be beneficial for you, so you can be explored there. Thank you very much for your attention, and this is my email address. So those who are interested to contact me, to collaborate me, to work with my team, okay, it's the most convenient way to communicate with me by this email. Sunway also has some engineering programs, some other programs, so we invite also to explore about Sunway University. Okay, thank you.
Okay, thank you, Prof, for the enlightened sharing just now on MXene. So we can basically summarize that MXene is an interesting nanomaterial that is versatile and holds such promises for future application. Before we proceed to the audience, please fill in the attendance link that has been posted in the chat box for your certificate. Now we open the floor for question and answer session. You can unmute your microphone to ask questions, or another way is to type your question in the chat box and I will read it to Prof. So I guess I've seen 2 questions in the chat box, Prof. Prof, I guess now you can turn on your camera.
Yeah, we can try now. So is it better now?
Yeah. We have already 2 questions in the chat box, for Prof.
Okay, yeah, so yeah, in chat box I can see, okay, I can read properly. Okay, so Amir Malik asked a question. I think that's a good question. So as you have seen in one of the slides, the structure image of max phase and MXene. So there are differences, and particularly the behavior of max phase is different. Their properties, as you have seen, spacing, their thermal conductivity, electrical conductivity, behavior properties are different than MXene. So basically, by eliminating that A layer, we are getting improved behavior, improved properties. So that's why that A layer need to be eliminated to get better behavior, better structure, better properties, better performances. Okay, so that's the reason. Okay, I think that's the basic question. Okay, I hope that answers your question. Second question, hydrophilic behavior of MXene. So my question is, do MXene experience similar degradation issues like black phosphorus? I have not seen the black phosphorus. I cannot answer that question. Sorry, I don't know whether the degradation there. Maybe we can study that, but I did not know. I don't have answer. I did not experience that degradation issues like black phosphorus. Okay, this need to be studied. As I mentioned, this is new area. Even though some of the findings are good, but still there are a lot of challenges. All those need to be overcome. So I attended Yuri Gogutsis and his other groups also. So they are also highlighting that, yes, there are some outstanding benefit behavior, but still some of the behavior need to be improved need to do work. A lot of work still need to be done. Okay, so as I have shown, it's hydrophilic, it's viscosity behavior, super lubricity. These are better, but what's the mechanism? All those details also still need to be done. So that's why a lot of research is going on, and we are also working towards that. Okay. So Dr. Tan also gave an answer. Dr. Tan is my colleague, as I have shown in some of the slides. He has gone through some of the training. He also published some paper. I think he gave some answer. I think that's good. That's the reason also I brought it here, because I have some knowledge. I don't have enough knowledge because this is so broad. So he will give some of the answer. Is what the purpose of getting high surface area like MXene. Okay, so I think you can read. That's a good top up. Thank you, Dr. Tan, for topping up in answering the questions. Okay, yeah, Dr. Azma, more questions if there is.
I've seen another one question below there, Prof. Is there any potential to use it for wastewater treatment?
Sorry, I cannot see that question. Can you repeat?
Is there any potential to use MXene for wastewater treatment?
Yes, it's for desalination, for removals of dyes, pollutants. As you have seen in one of the slides, adsorption behavior of MXene is very good because it has active surface, large surface area. So a lot of work is going on, water purification, desalination. It is very potential area. I forgot to highlight there, but there are.
Two more questions, Prof. I guess that is the two last questions that we can accept. How do you store your MXene samples? In vacuum desiccator or standard dry cabinet?
Yeah, Dr. Tan, maybe can you unmute and answer the question? This one, because Dr. Tan synthesized the MXene, so he can better answer. Okay, Dr. Tan, please.
Yeah, thank you, Prof. Thank you for the floor. Yeah, I'm Dr. Tan. Regarding the question of storing the MXene sample, right? There are a few methods. One of the very common method is, yeah, you can store it in the desiccator, because the main important issue is that you try to try to make the MXene get rid of oxygen. So basically, the common method is you can store it in desiccator. And another method is you can store it in the refrigerator, because we don't want the MXene that has been synthesized at a certain even room temperature, or maybe slightly higher than the room temperature, because there will be oxidation and further degrade the MXene. So it is highly recommended you store the MXene in the refrigerator at the room temperature. And then another alternative, you can actually use the MXene to be mixed with a certain organic substance, because the organic at the end will shield the MXene from the interaction of the oxygen. You can use a certain organic compound basically, because the MXene is very good. It can present in the aqueous, and also it can mix with the organic compound as well. So that's why one of the methods, you can use certain organic substance to make sure that the MXene will be get it in contact with the oxygen. So that's a few method. Yeah, Prof.
Okay, thank you, Dr. Tan. Yeah. Okay, so let me answer our students. One asked question about the stability. This is actually the major problem with any types of heat transfer fluid. I think this is the major challenge. A lot of techniques already tried, but with the MXene and graphene, is the difference is that graphene is hydrophobic, whereas MXene is hydrophilic because it has terminals, and also some of the using contact angle measurement, its hydrophilic nature is already found. That's basically is good for dispersion in water and some polar solvent. So some study already has been done, but still again, a lot of more studies needed, because this is the most challenging, most important area. And this stability is basically the work of chemists, material scientists. So they should be in the team. They should be involved in this research to overcome these challenges. So it can be done by surface modification. As you can see, the MXene is surface modification, surface improvement can be done. So there are some works still at the preliminary stage, but point is that it is hydrophilic in nature. That gives an indication that its dispersibility is better. Some research with maybe some emulsion, some other research already done, and they found it's good, stable. But in my view, still a lot of research need to be done on this area. This is actually the main drawbacks for commercial potentiality, this MXene. So this is the area need to be worked. A lot of works need to be done in this area. Okay, Wani?
Okay, thank you, Prof. I guess because of the limited time, so we have to stop the question and answer session here. We can now proceed to picture taking session. I would like to ask everyone to open your camera now.
I cannot open my camera.
Sorry to hear that. So,
Okay, just
yeah.
take picture of my blank screen.
My next time, please put your profile picture, Dr. Zul, so that at least there's a picture there.
It's
Okay,
okay.
so for other audience, please turn on your camera.
Sorry,
Who would like to
Dr.
take picture now?
Sorry, Dr. Asma.
Yes, yes.
I have one question to
Oh, yeah.
Prof. Saidur.
Okay. One last
Okay.
question. Okay.
Yes, teacher.
Yeah, okay, please.
Thank you, Prof. I have two questions. Why is your work focused on titanium carbide, 2-dimension? And what about the rest of the MXene types?
Yeah, okay. As you can see, this is the first material invented. So that's the curiosity, and it's not easy to develop, to synthesize other materials. So since it was invented 2011 and subsequently other materials, so that's why I think the focus is with the which one is available. And also this material is not commercially available. Synthesis process also tedious, as you have seen, huge high-end equipments are needed. Since this material was invented earlier, maybe many people also collaborate with Yuri Gogotsis and maybe other universities in China, US. I mean, availability, invention earlier. So these are the reasons. That's why extensively it has been studied. Definitely, as you can see, other researchers are also working and other materials are coming. Most important thing and challenging, it's basically a lot of challenges. So we started, in our lab, so we know how challenging to produce 1 gram. Even it has been invented in 2011. Some companies supply, as far as we know, some of our colleagues purchase it, but its purity is extremely poor, and then you cannot use it. So it's very challenging to produce these materials. So I think these are the reasons a lot of focus is on Ti3AlC2 or Ti3C2. Okay, and also comparison purpose. New material is invented, so its properties, behaviors, only few. Whereas Ti3AlC2 or Ti3C2, a lot of behavior properties are already there. So for comparison purpose also, when you hybridize, when you intercalate, when you made the heterostructure, I think for comparison purpose also it is good. So that's why I think that its main focus is there, but slowly other materials are also coming.
Thank you. That's clear. Thank you.
Thank you, Prof. Okay, Dr. Iza, are you ready to take the picture?
Yes,
Dr.
yes,
Iza?
yes,
Okay.
yes.
Everyone smile at the count of 3. 1, 2, 3. Okay, so do we have few
Next.
screens?
Okay, next.
Iza?
Yes,
Okay,
second
next
screen,
one.
please.
Second screen, smile. 1, 2, 3.
Okay, done.
Okay, do we have a third screen?
No, we have 2
Just
screens
two.
only.
Okay. All right, thank you, Dr. Iza. Okay, unfortunately, time flies so fast when we are having fun learning. So if you have more questions, to Prof. Saidur, please do contact Prof. Saidur directly on the using the information that he have given before. But his contact information is also available on our department's website under the academic staff information portal. On behalf of the organizing committee, we would like to apologize for the glitch that we had throughout the meeting, the event. Thank you, Prof. Saidur. Again.
All right, Prof. Thank you, Prof.
Thank you for being
Thank you,
Thank you,
team
Prof.
participants.
All right. See you
Thank you.
later.
Assalamualaikum.
Assalamualaikum.
See you later.
Thank you for your
All the
time and
best.
attention. Okay, please
Bye.
take care, stay safe, and have a nice day. Thank you, guys. Bye.
Thank you. Assalamualaikum.
Thank you.
Salam.
Assalamu alaikum.